So in this slide, we're going to talk about the utilization of the central finite difference method into to solve two-dimension heat conduction problem. It's very typical to what we did before for the first one-dimension problem. A few examples that we covered before. I'm going to go through the general procedure. Maybe later on we can look into an example, but again, these are all introduction to the basic content that we're looking to cover, which is the finite volume method. But I'm taking you step by step to learn how to move from one-dimension finite difference method, two-dimension finite difference method. Then we add complication to it before we jump into the finite volume method. What's going to happen in two-dimension problem now, instead of having just node available to the right of your base point, you will have additional nodes. So we have, this is node I. In one dimension, we only needed the I plus 1 and I minus 1, one after and one before. Either you are using the forward, backward, central finite difference. And as I mentioned, that central finite difference provide less error because of the order of the error of the value of h squared. So it's more accurate compared to the forward or backward one. In the two-dimension case, I will have now j plus 1, and I will have j minus 1. That's the case now. So now, if we like to solve two-dimension conduction problem, your governing equation, your model will be actually the Laplace equation, partial 2t by partial x squared plus partial 2t by partial y squared. Now, if you are solving with no heat source, the equation will end by equal 0. If you have a heat source, you have to add another term, which is q dot over k equal to 0. Very similar to what we did in the one-dimension problem. And in this case, instead of only using the approximation of the central finite difference method for the x direction, which is ti plus 1 minus 2 ti plus 2t, plus ti minus 1 divided by delta x squared, whereas delta x is the span between the nodes like this. And now you will need the approximation for partial 2t by partial y squared. At the same node I is going to be t j plus 1 minus 2 of t. I like to keep it I all the time, so I know that these are referring to the same base node I'm interested in. Plus tj minus 1 divided by, this is delta x squared, this is delta y squared. So if you substitute into the original equation, the Laplace equation, you end up having ti plus 1 minus 2 ti plus ti minus 1 divided by delta x squared plus t j plus 1 minus 2 ti plus t j minus 1 divided by delta y squared equal to 0. Now, if you want to simplify this equation, again, if you have a heat generation term or heat source term, you're going to add q dot over k in case you have this into that problem. Now you need to simplify this equation. And the simplest way to simplify this equation, which is your choice, it's your call, you decide that, is to pick delta x and the delta y are equal distance. So when you are meshing or gridding your domain, if you have a control to pick up delta x and delta y are equal, this will be great. Delta y is that vertical distance here, equal to this one here. So I picked up delta x and delta y are equal. So you multiply the equation by delta x squared, you will have ti plus 1 minus 2 ti plus ti minus 1 plus delta x squared and delta y squared are equal. So it's going to go away. Tj plus 1 minus 2 ti plus tj minus 1 equals 0. Let's actually combine the same terms here. You will find yourself having ti plus 1 plus ti minus 1 plus tj plus 1 plus tj minus 1 minus, this will give you 4 of the node ti equals 0. Look at this equation here. So this is for node I. So for node I in two-dimension problem, it is simply you are adding up the temperature or the value, the variable for the node surrounding your base one, I plus 1, I minus 1, j plus 1, j minus 1, minus for the 4 times the node of interest, the base node equals 0. Please keep in mind this equation is valid under this only condition here. If this condition is not valid, if delta x is selected to be different than delta y, these two values will not cancel out, and you will have a multiplication factor for a few of these terms. Okay, but again, if that's something we can control, we will go that route. So that's the equation you can get. Then this is an equation for what we call interior node. This is a node sitting inside a solid domain surrounded by equivalent nodes. Then one would say, okay, what will happen if the heat generation terms exist? What's going to happen? Actually, you will find yourself, there is all q dot over k is in here. You will find an extra term q dot over k in here. Here, remember, you multiply by delta x squared, right? So there is cancel out from here, but it's not going to cancel out from here. So you'll find yourself adding q dot delta x squared over k. Remember, q delta x squared, it's simply q dot times the volume. It's delta x times delta y times the depth. So this is originally delta x times delta y times the depth. And we agreed in the finite difference method, the depth is always assumed 1. And delta x and delta y, we are assumed they are the same. That's why it's ended up to be delta x squared times 1. And this is simply the volume of the control element surrounding your node. You remember, we draw a square. This is delta x, this is delta y. So that's the control element. You end up having this. So an additional term will be added if you are solving with heat source into that two-dimension problem. That's how you apply the central finite difference method into a two-dimension issue. So the question is, can we apply the energy balance method into this? Yeah, the answer is yes. Let's see how to use two-dimension conduction using the energy balance method. And you should get exactly the same equation for node I here, either you have a heat source or not. So I will state here, two-dimension conduction, but I'm going to use energy balance method. Here is my domain. And again, I try to keep delta x, delta y equally. So that's my delta x. That's my delta y. Now, this is my node I. I'm surrounded by I plus 1, I minus 1, j plus 1, and j minus 1. Now, what I'm going to do for the energy balance method, I'm going to draw my control volume, which is a square of the dimension delta x, delta y, and we keep them almost the same. So that's going to be my square. That's my affecting domain of node I. That's my square. Okay, this is delta x, this is delta y. Now I'm going to supply all the energy into that control element. So I'm expecting to have heat coming that way, or energy coming that way, energy coming that way, and energy coming that way. So Q1, Q2, Q3, Q4 are supplied into the control volume, and all of them are coming into that control volume or control element. It's because this is the assumption of the energy balance method. Now, the equation is E dot in plus E dot generated equal to E dot out plus E dot stored. Now, if I assume there is no heat source here, this is 0 for a steady state. This is 0 because it's against the assumption of the energy balance method. And this is because there is no heat source. If there is heat source, we will add that later. So the equation said that the energy in should equal 0, right? This will lead to all the energy in equal 0. So now I have Q1, Q2, Q3, and Q4. Then you're going to add up all of these Qs and to present the energy N. So Q1 is coming by conduction. It's going to be Ka, then multiplied by the Ti minus 1 minus Ti divided by the distance, which is delta X. And by the way, the area as defined in Fourier's law is the area perpendicular to the direction of heat. So A here is presenting that height, which is delta Y. So I'm going to write that delta Y. So that's going to be K delta Y, height, times the depth, which is 1, multiplied by Ti minus 1 minus Ti divided by delta X. Second equation, which is Q2, this will be simply K. The area is going to be delta X times 1, Tj plus 1 minus Ti divided by the distance between the two nodes is delta Y. Q3 is going to be K. The area is delta Y times 1, Ti plus 1 minus Ti divided by delta X is the spacing distance between the two nodes. And the last Q that's coming from the bottom here, it's K. The area is going to be delta X times 1 times Tj minus 1 minus Ti divided by delta Y. Again, for simplicity, we choose delta X equal delta Y. If it is not, you have to be careful when you simplify that. If you do that, you'll find this will cancel out, this will cancel out, this cancel out, this cancel out. So I'm going to end up having K times this term, K times this term, K times this term, K times this term, and I'm adding up all of them and equals 0. I can take K as a common factor, right? So I'm going to have K, and the first term will be Ti minus 1 minus Ti plus Tj plus 1 minus Ti plus Ti plus 1 minus Ti plus Tj minus 1 minus Ti, and this is totally equal to 0. So K will goes away. Now you simplify that, you will have Ti plus 1, which is this term, plus Ti minus 1, which is this term, plus Tj plus 1, which is this term, plus Tj minus 1, which is this term, and I have Ti once, twice, 3, and 4 times. So that's 4 minus 4 Ti equals 0. If you look to that equation, this is the equation for node I. If you compare that to what we got from discretization of the Laplace equation, it's exactly the same equation. Okay? Now, what if the Q dot term is present? If the Q dot term is present, this means that this term E dot G will not be equal 0. So you will have, after you take that as a common factor, you will have here Q dot times the volume. That's what E generated is. Q dot times the volume of the control element, which is delta X times delta Y. So this will be actually Q dot delta X delta Y times 1. So you will find that term is added here, and you'll end up having another term here that's Q dot delta X squared, because delta X and delta Y are selected to be the same, divided by that K, it's not going to go away, equal 0, which is very exactly the same term that's added here, right? So you either use the direct discretization of the Laplace equation, that's fine. If you use the energy balance method, it's also fine. Both will lead to the same equation here. So this is how you use the finite difference method, centralized situation, or the central finite difference method, and the energy balance method to collect information for two-dimensional heat conduction problem for nodal equation. Then you apply that for all the nodes to get the answer that you're looking for. Okay, now the two-dimension problem has many cases. So if you go back to one of your heat transfer reference books, you'll find there are tables that already exist. This is the case that we just drove the equation for. Unfortunately, the book here is fundamental of heat transfer with I think it's Incropera, the author, but it's using different symbol, so it's using M and N instead of I and J. And I'm bringing that table here to show you the information is available and you have to dig to find it. So this is the case. We just drove the equation, and you see that it's simply the node to the right, the node to the left, the node to the top, the node to the bottom minus 4, the base node equals 0, and this is the same equation. So again, and this book is clearly showing that all the derived formula here is for delta x equal delta y. If they are not equal, you have to go slowly from the beginning and cannot use directly this equation. If you assume delta x equal delta y, you can directly use the equation, that's fine. Okay, so now what if you have a body with cutted core here, and you would like to get an equation for this node, and this is the equation for that node if that node is exposed to convection here. So the table is available. You can use it as is if you have these cases part of your problem. This is a surface point exposed to convection. You can simply take that equation and use it. So you don't have to drive the equation if you are solving a problem and you are exposed to one of these cases here. Here, a fully interior point, point at corner exposed to convection, point at face exposed to convection, another corner exposed to convection, and this is when the surface is exposed to heat flux. So feel free to pick up this equation directly if it is satisfying the point or the nodal that you're looking for. And keep in mind, delta x and delta y are assumed to be the same. So that's the beauty about these tables. And I guess now using finite difference method or energy balance method in two-dimension problem shouldn't be any problem. And again, the tables is available. You can find them anywhere, and you are free to use these tables as long as they are satisfying the condition set up by the book to drive these equations. What would be the next level if you are thinking about how to use finite difference method or any other discretization method into heat transfer problem? I think the next logic step is, can we solve actually two things? Can we solve transient problem? So all the solution that we did so far in all the examples is only covering steady state. Can we utilize finite difference method to solve transient problem, time-dependent problem? That's number one. Number two, can we use finite difference method to solve other coordinate than x, y, and z, other than the Cartesian coordinate? Can we use the finite difference method to solve radial system, spherical coordinate, cylindrical coordinate, either it's steady or unsteady? So that's what we're going to answer in the upcoming few slides.